using their R values in their ability to be a good insulator, in their ability to allow heat to pass through. That is the R value. Now, if two conductors of thermal resistances R1 and R2 are arranged in series. Now, how do we arrange two materials in series? Now, this is the arrangement of two materials in series. It means heat has to pass through one material and then through the other. So, combining materials in series will increase their thermal resistance. Is that right? Yes. So, thermal resistors are arranged in series like this. If the heat flows through the first, it then has to go through the second. That means the thermal resistance is increased. The total thermal resistance, therefore, is the sum of the two thermal resistors. This kind of an arrangement is called a series arrangement. A series arrangement. So if you want to have a very good thermal insulation, you arrange the insulators in series. Now, if you live in very cold climate, you know, windows are double glazed. In other words, there are two layers of glass and a layer of air in between. You know that air is a very good insulator. That means glass, air, glass, there are three materials in series. The heat has to pass through these three materials. You are increasing the thermal resistance so that it becomes a very good insulator. On the other hand, if they are arranged in parallel like this, that means heat can pass through either the first one or the second one. That means you are reducing the thermal resistance. A parallel arrangement will reduce the thermal resistance. If the total resistance is R, then 1 over R equal to 1 over R1 plus 1 over R2. We will see the same kind of arrangement of resistors in electricity. Well, we will look at that shortly, well, maybe a few weeks from now. Let's do a small problem. A copper bar 2 meter long has a circular cross-section of radius 1 centimeter. One end is kept at 100 degrees Celsius and the other end is kept at 0 degrees Celsius. The surface of the bar is insulated so that there is negligible heat loss through it. That means there is no heat loss through the surface. Heat passes through the material. Find 1, the thermal resistance of the bar. Well, if you know that formula, can you tell me what is the formula for thermal resistance? Isn't it delta X over Ka? Well, find the thermal resistance of the bar, find the thermal current, the temperature gradient, and the temperature of the bar 25 centimeter from the hot end. Alright, let's see what the given things are. We got a copper bar 2 meter long, delta X equal to 2 meter. We use delta X for the length. One end is at 100 degrees Celsius, the other end is at 0 degrees Celsius. What is the drop in temperature? Will be 100 minus 0. And the radius of the copper bar is like this, what I'm holding here. It is, can you see this? Well, I'm trying to see if I can put it above the light. But, well, the end is circular. The radius of this circular part is 1 centimeter, that is 0.01 meter, And what do you need the radius for? That will help us to find the area of cross-section. What is the area of cross-section if the area of cross-section is a circle? Well, that will be pi r squared, is that right? And this is a copper material, and K, the thermal conductivity for copper from our tables, is 401 watt per meter per Kelvin. The area of cross-section of the bar is pi r squared, where r is 0.01 meter, and so that's equal to 3.14 times 10 to the negative 4 meter squared. So now you know the length of the copper rod, we know its area of cross-section, we know the drop in temperature, we know the value of K, we practically know everything that we need. What is the thermal resistance R? This must be an uppercase R, not the lowercase r. The thermal resistance is R equal to delta X divided by Ka. We've got delta X, we've got K, and we've got A. Let's place those values there and calculate. Now you need to do all these calculations on your own. Always remember to keep a calculator, paper and pencil with you when you listen to the lecture. Alright, I got that value as 15.88 Kelvin per watt, and that is the thermal resistance. Well, we know the thermal resistance, we know the temperature difference delta theta. Can you use that to find the thermal current? What is the equation that we obtained for thermal current? Well, what is the equation we obtained for the temperature difference delta theta? Delta theta equal to I times R, where I is the thermal current and R is the thermal resistance. Delta theta equal to I times R. Therefore, I equal to delta theta divided by R. Delta theta is 100 minus 0, and R we just calculated. So the thermal current is 100 Kelvin divided by 15.88 Kelvin per watt, and that is 6.3 Kelvin per watt, and the thermal resistance is Kelvin per watt. Kelvin and Kelvin cancels, watt will go up, so you can see thermal current is 6.3 watt. What is our next part? The temperature gradient. What is the temperature gradient? Delta theta divided by delta X. And we know both those values. 100 Kelvin divided by 2 meter, that is 50 Kelvin per meter. What does that mean? As we go down from the hot end towards the cold end, the temperature will fall at the rate of 50 Kelvin per meter. So when it comes to 1 meter, the temperature will be 50 degrees Celsius. You see? There is a fall in temperature of 50 degrees per meter. We can use now that concept to find the next part. We want to find the temperature at 25 degrees from the hot end. What will be the temperature 25 degrees from the hot end? Knowing that the temperature gradient is 50 Kelvin per meter. Well, that will be 100 minus 50 Kelvin per meter multiplied by 0.25. Is that right? Because as you go down, the temperature will fall at the rate of 50 Kelvin per every meter. So the amount of fall will be the rate multiplied by the length. So 100 minus 50 Kelvin per meter times 0.25 meter, The temperature 25 centimeter from the hot end is 87.5 degrees Celsius.